Hello there and welcome to the Sleepy Science Channel. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to the quiet sound of rain rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow heavy and warm, like a stone settled at the bottom of a slow river. Because tonight, we aren't simply listening to rain fall against a window. We're following it, down through clouds into rivers beneath the ground and out to the wide, patient sea. Water is the oldest traveler on Earth, older than mountains, older than forests, older than almost everything that lives and breathes upon this planet. It has fallen as rain more times than we can count, and it will fall again long after we are gone. Tonight, we'll drift gently through its story. The clouds that carry it, the rivers that carve their way through stone, the hidden water that moves beneath our feet in total darkness, and the quiet, eternal cycle that connects a raindrop on a mountainside to the deepest trench in the ocean. Some of what you hear tonight may surprise you, or at the very least, settle over you like a soft and steady rain. And just before we begin, if these calm, curious explorations help you drift off, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time, drop by drop. Now let's begin. Every raindrop that falls today has fallen before. Water on Earth is ancient, far older than any living thing. The same molecules of water that once filled the oceans of a much younger planet are still here, cycling endlessly through cloud and river and sea. Nothing is created, and almost nothing is lost. A raindrop that lands on your roof tonight may have once been part of a glacier, or a puddle beneath the feet of a creature that lived long before recorded time. It has been vapor rising off a warm sea, and ice locked for centuries at the poles, and dew resting quietly on a blade of grass at dawn. Water does not begin or end. It only changes shape, drifting through an endless, patient cycle that connects every era of the planet's long history into a single unbroken thread. The water cycle is older than life itself. Long before the first living cell stirred in some shallow, ancient pool, water was already rising as vapor, gathering into clouds and falling again as rain. The early Earth was a violent place, scorched by volcanic heat and struck by comets and asteroids carrying ice from the outer edges of the solar system. Slowly, as the planet cooled, water vapor condensed into rain that fell for what may have been thousands of years without pause, filling the basins that would become the first oceans. This first great rainfall shaped the surface of the planet before anything alive was here to feel it fall. In a very real sense, water arrived before life did, and prepared the world so that life could begin. Rivers carve time into stone. A river's power seems gentle when you watch it drift by, calm and unhurried, catching the last light of evening. But given enough time, that same gentle water can cut through solid rock, grinding stone into sand one quiet moment at a time. The Grand Canyon did not appear suddenly. It was carved slowly, patiently, over roughly 6 million years, as the Colorado River wore down layer after layer of ancient rock, exposing a record of Earth's history nearly 2 billion years deep. Every bend in a river, every canyon wall, is a kind of clock, one that measures time not in seconds or centuries, but in the slow persistence of moving water against unmoving stone. The ocean holds nearly all of Earth's water. If you gathered every drop of water on the planet, from oceans to rivers to clouds to ice, you would find that the oceans alone hold about 97% of it. Only a small fraction remains as fresh water, and of that fraction, most is locked away in glaciers and polar ice, far from reach. The rivers, lakes, and rain that sustain life on land make up only a sliver of this vast total, a thin and precious layer resting atop an overwhelming sea. When you watch rain fall, you're witnessing a brief visit, a small portion of that endless ocean, borrowed for a while, before it eventually finds its way home again. Groundwater flows in hidden rivers beneath us. Not all rivers are visible. Beneath the surface of the Earth, Water moves slowly through layers of rock and soil, filling spaces between grains of sand and cracks in stone. These underground reservoirs are called aquifers, and some of them stretch for hundreds of miles, invisible highways of water flowing in near total darkness. Unlike rivers on the surface, groundwater can take decades, centuries, or even thousands of years to travel from one place to another. Some of the water resting in deep aquifers today fell as rain before the pyramids were built. It has been moving, quietly and without complaint ever since, drop by drop, through stone that remembers a much older world. Clouds are rivers in the sky. It's easy to think of clouds as something separate from water on the ground, soft white shapes drifting far above us. But every cloud is, in its own way, a river suspended in the air, carrying enormous quantities of moisture from one place to another. Some storm systems transport more water through the atmosphere in a single day than the largest rivers on Earth carry in a month. These invisible rivers in the sky, sometimes called atmospheric rivers, can stretch for thousands of miles, pulling moisture from warm tropical oceans and delivering it as rain or snow to distant coastlines. The sky above you tonight may be part of one of these vast, invisible currents, quietly moving water across the entire planet while you sleep. Rain begins as ice, even in summer. High above the ground, even on the warmest days, the upper reaches of a rain cloud are often cold enough for ice to form. Tiny ice crystals gather moisture as they drift, growing heavier until they begin to fall. As they descend into warmer air near the ground, they melt, arriving at your window not as snow, but as rain. In this way, nearly all rain begins its journey as something closer to snow, transformed along the way by the changing temperature of the air it falls through. Even a warm summer rain carries within it a memory of ice, a quiet reminder of how cold the sky can be, just a few miles above where you rest tonight. The longest rivers carry memories of continents. Rivers like the Nile, the Amazon, and the Yangtze do more than move water. They carry with them the story of entire continents, gathering rain and snowmelt from thousands of tributaries and carrying it, sometimes for thousands of miles, toward the sea. Along the way, they pick up sediment worn from distant mountains, carrying tiny fragments of stone that may travel farther in a single year than most living things travel in a lifetime. A grain of sand resting in the Nile Delta today may have once been part of a mountain deep in the heart of Africa, broken down slowly by water and carried, patiently, toward the coast. In this way, a great river is not simply a body of water, but a moving archive of the land it passes through. Water shaped the first civilizations. Long before written history began, the earliest human settlements gathered near rivers. The Tigris and Euphrates cradled the beginnings of Mesopotamia. The Nile gave rise to ancient Egypt. The Indus nurtured one of the first great urban cultures, and the Yellow River became the birthplace of early Chinese civilization. Rivers offered fresh water for drinking, fertile soil for farming, and a means of travel and trade that connected distant communities. The rhythm of these rivers, their floods and their droughts, shaped calendars, religions, and entire ways of life. In many ways, the story of human civilization is also the story of water, and the quiet decision, made again and again across the ancient world, to settle beside a river and build a future around its flow. The deepest parts of the ocean remain unmapped. Despite covering more than 70% of the Earth's surface, the ocean remains one of the least explored places on the planet. More people have traveled to space than have descended to the deepest point of the ocean floor, a place called the Challenger Deep, nearly 7 miles beneath the surface. Down there, in complete darkness and under crushing pressure, water still moves in slow, cold currents, carrying nutrients and life to places sunlight will never reach. Scientists estimate that we have mapped only a small fraction of the ocean floor in detail. Beneath the waves that rock gently along familiar coastlines lies a vast, largely unseen world, still waiting patiently to be discovered. Rivers change course over centuries. A river's path may seem fixed on a map, but given enough time, rivers wander. Slowly, over decades and centuries, a river will erode one bank while depositing sediment on the other, gradually shifting its entire course across a floodplain. Some rivers have moved their mouths by dozens of miles over the span of a few thousand years, abandoning old channels and carving new ones. The Mississippi River, for example, has changed its path to the sea several times over the last several thousand years, each shift leaving behind traces of its former route in the shape of the land. A river is never truly still. It is always searching, however slowly, for a new way home. Snow is frozen rain, delayed. When the air near the ground is cold enough, the same moisture that would otherwise fall as rain instead reaches us as snow, each flake a small, intricate crystal formed as water vapor freezes directly around a tiny particle of dust high in the clouds. No two snowflakes are exactly alike, shaped by the precise humidity and temperature they encounter as they drift downward. And yet, snow is simply rain that has taken a colder, slower path. When it eventually melts, whether in the same season or the next, it rejoins the same endless cycle, flowing into streams and rivers, continuing a journey that began, in truth, no differently than any drop of summer rain. The Amazon River pushes fresh water far into the ocean. The Amazon carries such an enormous volume of fresh water that its influence can be detected far out at sea, sometimes more than 100 miles from the coast of Brazil. Sailors in earlier centuries reported being able to drink fresh water from the ocean's surface long before they could see land. So powerful was the river's outflow. This vast plume of fresh water forms a layer atop the denser salt water of the Atlantic, visibly changing the color of the sea for a great distance offshore. It is a striking reminder of just how much water a single river system can hold, a slow green flood pouring quietly and endlessly into the waiting blue of the ocean. Aquifers are ancient, slow-moving reservoirs. Beneath many of the driest regions on Earth lie aquifers containing water that fell as rain thousands, even tens of thousands of years ago, during periods when the climate was far wetter than it is today. The Nubian Sandstone Aquifer, stretching beneath parts of Egypt, Libya, Chad, and Sudan, holds water that has been resting underground since the last ice age. This fossil water, as it is sometimes called, moves so slowly through the rock that it may take thousands of years to travel just a short distance. In the quiet dark beneath the desert sand, ancient rain continues its unhurried journey, a slow and patient memory of a wetter world. Rain smells like petrichor, released from soil. The distinctive earthy scent that rises after a rain shower has a name: petrichor. It comes from a combination of oils released by plants during dry periods, compounds produced by soil bacteria, and ozone carried down by the storm itself. When raindrops strike dry earth, they release these trapped scents into the air, carrying them upward on tiny bursts of aerosolized soil. This smell, so familiar and so calming to many people, is in a sense the scent of water reuniting with land after a long absence, a quiet chemical signal that the dry spell has ended, and the cycle continues once more. Waterfalls are rivers pausing in freefall. A waterfall may seem like the dramatic climax of a river's journey, but it is really just a brief and thunderous pause, a place where the land drops away and the water is forced to fall rather than flow. Most waterfalls form where softer rock erodes faster than the harder rock above it, leaving behind a ledge over which the river must leap. Over time, this constant erosion causes waterfalls to slowly retreat upstream, carving a gorge behind them as they go. Niagara Falls, for instance, has been retreating upstream for thousands of years, moving slowly backward even as it roars forward, a paradox written patiently into the rock beneath it. The Nile shaped an entire civilization's calendar. For thousands of years, the flooding of the Nile River was so reliable that ancient Egyptians built their entire calendar around it, dividing the year into 3 seasons based on the river's rhythm: the flood, the growing season, and the harvest. Each summer, monsoon rains far to the south. in the highlands of Ethiopia would swell the river until it overflowed its banks, depositing a fresh layer of dark, fertile silt across the surrounding fields. This annual gift of rich soil allowed Egyptian agriculture to flourish for millennia in an otherwise arid landscape. The river's floods were so central to survival that they were worshipped, measured, and celebrated. A distant rainstorm transformed into the very heartbeat of a civilization. Deltas are rivers surrendering to the sea. As a river nears the ocean, it slows, and the sediment it has carried for hundreds or thousands of miles begins to settle out, building new land grain by grain. Over centuries, this process forms a delta, a wide, fan-shaped landscape of channels, marshes, and islands, all constructed patiently from material the river once tore from distant mountains. The Mississippi Delta, the Nile Delta, and the Ganges Delta are all, in a sense, the final resting places of countless mountains, worn down over ages and reassembled at the edge of the sea. A delta is where a river's long journey ends, not abruptly, but in a slow and graceful surrender to the wider water beyond. The driest deserts still have underground water. Even in places where rain almost never falls, water often exists just beneath the surface. The Atacama Desert in Chile, one of the driest places on Earth, still holds pockets of underground moisture that support scattered, hardy life. Ancient aquifers, formed during wetter periods thousands of years ago, continue to sustain oases scattered across the world's most arid landscapes. These hidden reserves remind us that the absence of rain does not always mean the absence of water. Sometimes it simply means water has gone quiet, waiting patiently beneath the surface for its moment to rise again. Glaciers are frozen rivers moving in slow motion. A glacier may look like a still and frozen mountain of ice, but it is, in truth, a river, moving under the pressure of its own weight, however slowly. Some glaciers creep forward only a few inches a year, while others, called surging glaciers, can move dozens of feet in a single day. As they move, glaciers carve valleys, grind boulders into fine powder, and carry rock debris for miles before depositing it far from where it began. Many of the world's most dramatic landscapes, from fjords to U-shaped mountain valleys, were shaped not by rushing water, but by the slow, relentless progress of ancient ice, rivers so patient they took thousands of years to carve what they carved. Monsoons are the breathing of continents. Twice a year, across large parts of Asia, Africa, and northern Australia, the wind reverses direction entirely, drawing moist ocean air deep into the continent during one season and pushing it back out to sea during another. This seasonal shift, known as the monsoon, brings enormous quantities of rain to regions that depend on it for agriculture and daily life. In India alone, the summer monsoon can deliver nearly 80% of the country's annual rainfall in just a few months. It is, in a way, the slow, seasonal breathing of an entire continent, inhaling moisture from the sea and exhaling it again as rain across the land. Estuaries are where fresh and salt water meet and mix. At the mouth of many rivers lies an estuary, a place where fresh river water gradually blends with the salt water of the sea. These transitional zones are among the most biologically rich environments on Earth, supporting nurseries for fish, resting grounds for migratory birds, and delicate ecosystems that depend on the shifting balance between fresh and salt water. The mixing is never simple. Tides push salt water inland, while river currents push fresh water outward, creating complex layers and gradients that change with the rhythm of the moon. An estuary is a quiet negotiation between river and sea, conducted patiently, twice a day forever. Thunderstorms recycle enormous amounts of water in minutes. A single large thunderstorm can release millions of gallons of water in the span of an hour, water that was drawn up from the surface as vapor, sometimes from an ocean hundreds of miles away, condensed into towering clouds, and then released again as rain, hail, or wind-driven sheets of water. The energy involved in this process is immense, equivalent to that of a small explosion, repeated over and over as the storm moves across the land. Within the swirling chaos of a summer storm lies one of nature's fastest and most powerful demonstrations of the water cycle. An entire journey from ocean to sky to ground compressed into a single, dramatic hour. Some rivers flow underground entirely. Not every river remains on the surface for its whole journey. In regions with soft limestone bedrock, rivers can disappear entirely into sinkholes, continuing their path through vast underground cave systems before re-emerging, sometimes miles away, through hidden springs. The Rio Puco in New Mexico and sections of rivers throughout the karst landscapes of Slovenia and China vanish underground for stretches, flowing silently through caverns untouched by daylight. These hidden rivers carve stunning cave systems over thousands of years, decorated with formations built one mineral-laden drop at a time. Somewhere beneath your feet tonight, in caves across the world, rivers are still flowing in complete darkness, unseen and unheard by anyone above. The water you drink today may be as old as the dinosaurs, because water is neither created nor destroyed in any significant way on Earth. The same molecules have been cycling through clouds, rivers, oceans, and living things for billions of years. It's entirely possible that some of the water in your body today once fell as rain during the time of the dinosaurs, or passed through the body of a woolly mammoth, or drifted as vapor above an ocean that no longer exists in its ancient form. Every glass of water carries with it a nearly unimaginable history, a story stretching back through the deepest layers of geological time, quietly present in something as ordinary as a sip of water before bed. Wetlands are the kidneys of the landscape. Marshes, swamps, and bogs may not seem as dramatic as rushing rivers or towering waterfalls, but they perform one of the most important roles in the water cycle. As water moves slowly through a wetland, sediments settle, excess nutrients are absorbed by plants, and pollutants are gradually filtered out, cleansing the water before it continues downstream. Wetlands also act as enormous sponges, soaking up floodwaters during storms and releasing them slowly afterward, softening the impact of both drought and flood. Quiet, still, and often overlooked, wetlands are the land's own patient filtration system, working steadily beneath a calm, undisturbed surface. Rainforests generate their own rain. In the heart of the Amazon, much of the rainfall does not come from distant oceans at all, but from the forest itself. Trees release enormous quantities of water vapor through their leaves in a process called transpiration, and this moisture rises, condenses, and falls again as rain, sometimes many times over before it ever reaches a river. Scientists estimate that a single water molecule may be recycled through the Amazon's trees and skis as many as 5 or 6 times before completing its journey to the sea. In this way, the rainforest doesn't merely receive rain, it creates it, breathing moisture upward into the clouds in a slow, continuous exchange between forest and sky. Rivers are always changing their path, meandering. Left undisturbed, a river rarely runs in a straight line. Instead, it curves and winds across the land in a series of graceful bends called meanders, formed as water erodes the outer edge of each curve while depositing sediment along the inner edge. Over time, these curves grow more pronounced, looping back on themselves until, occasionally, the river cuts through a narrow neck of land, straightening its course and abandoning the old bend entirely. This constant, gentle wandering is not a flaw in the river's design. It is simply how water finds its way, curving and adjusting endlessly in search of the easiest path to the sea. The deepest lakes hold water older than nearby rivers. Lake Baikal in Siberia, the deepest and oldest lake in the world, holds water that has been resting in its basin for a remarkably long time, layered and mixed slowly over centuries. Because of its extraordinary depth, over a mile at its deepest point, water near the bottom of the lake can remain largely undisturbed for long stretches, cycling far more slowly than the rivers that feed it. Ancient, cold, and clear, Lake Baikal holds nearly 20% of all the unfrozen fresh water on Earth's surface, a vast and quiet reservoir resting patiently in the heart of a remote and largely untouched wilderness. Icebergs calve from ancient glaciers. When a glacier reaches the sea, enormous chunks of ice can break away in a dramatic process known as calving, crashing into the water and drifting free as icebergs. Some of these icebergs contain ice that formed from snow that fell tens of thousands of years ago, compressed over time into dense, ancient ice far older than any living thing on Earth. As an iceberg drifts and slowly melts, it releases water that has been locked away since long before recorded history began, quietly rejoining the ocean after an absence measured not in years, but in ages. The color of rivers tells their story. A river's color is rarely accidental. The milky, pale gray of glacial rivers comes from finely ground rock flour, sediment so fine it stays suspended in the water, catching and scattering the light. The reddish-brown tint of blackwater rivers in the Amazon comes from tannins released by decaying leaves and plant matter, steeping the water much like tea. Clear, blue-green mountain streams often carry very little sediment at all, allowing sunlight to pass deep into the water and reflect off the pale stone below. Every shade of every river is a quiet signature, a visible record of the land it has passed through and the story it carries downstream. Underground rivers exist beneath deserts. Beneath the Sahara and the deserts of the Arabian Peninsula lie vast underground rivers and aquifers, remnants of a much wetter climate that existed thousands of years ago. The Disi Aquifer beneath Jordan and Saudi Arabia, and the Nubian Aquifer beneath North Africa, hold ancient water that continues to slowly seep through rock layers, occasionally reaching the surface in scattered oases. These underground rivers move so slowly, sometimes only a few feet per year, that scientists can trace their flow using isotopes left over from rain that fell during the last ice age. Far below the shifting sand, in total silence, ancient water continues a journey that began long before the desert above it ever existed. Floods reshape landscapes in hours. While rivers usually carve the land slowly, floods can accomplish in a single day what might otherwise take centuries. When water rises beyond a river's banks, it can move enormous quantities of sediment, topple trees, redirect channels, and deposit new layers of soil across floodplains in a matter of hours. Ancient farmers understood this well, timing their planting to follow the retreat of floodwaters that left behind fresh, fertile silt. Floods are often remembered as disasters, and they can be. But they are also one of nature's fastest and most powerful forms of renewal, a brief and forceful reminder of just how much change moving water can bring. Raindrops are not tear-shaped. Despite how they're so often drawn, raindrops are not shaped like teardrops at all. Small raindrops are nearly spherical, held together by surface tension. As they grow larger and fall faster, air resistance pushes against the bottom of the drop, flattening it into a shape more like a tiny hamburger bun than a teardrop. If a raindrop grows too large, it becomes unstable and breaks apart into smaller drops before it ever reaches the ground. The gentle patter you hear against a window at night is the sound of countless soft, round shapes, not falling tears, but tiny spheres of water completing the final seconds of a journey that began far above the clouds. Storm clouds can hold enormous weight of water. A single large cumulonimbus cloud, the kind responsible for thunderstorms, can hold hundreds of thousands, even millions of tons of water in the form of tiny suspended droplets. These droplets are so small and so evenly distributed that the immense weight of the cloud is held aloft by rising currents of warm air, invisible pillars strong enough to support what would otherwise plummet instantly to the ground. When these updrafts weaken, or when droplets combine into larger, heavier drops, gravity finally wins, and the rain begins to fall, releasing all at once a portion of a weight that had been quietly suspended above us the whole time. Rivers meet the sea in many different ways. Not every river ends the same way. Some, like the Amazon, pour directly into the open ocean with tremendous force. Others slow gradually into wide, branching deltas, splitting into dozens of smaller channels before reaching the sea. Some rivers form long, narrow estuaries, stretching for miles as fresh and salt water gradually blend. Still others, in dry climates, never reach the sea at all, disappearing instead into desert basins or shrinking lakes. Each of these endings tells a different story about the land the river has crossed, the climate it has passed through, and the balance between the water it carries and the thirsty land around it. The source of a river often begins as a tiny spring. It's easy to imagine a great river beginning dramatically, but most rivers start humbly, as a small spring bubbling up from the ground, or as melting snow trickling down a mountainside. The Mississippi River, which eventually grows wide enough to carry ships, begins as a narrow stream in Minnesota, one you could easily step across. The Amazon's most distant source has been traced to a small glacial stream high in the Andes Mountains of Peru. Every great river, no matter how wide or powerful it eventually becomes, begins as something small and quiet, a single thread of water finding its way slowly downhill. Watersheds connect distant lands. Every drop of rain that falls belongs to a watershed, a defined area of land where all the water drains toward a common river, lake, or sea. Watersheds can be small, covering a single valley, or immense, spanning multiple countries and thousands of miles. The Mississippi River watershed drains water from all or part of 32 American states and 2 Canadian provinces, meaning rain falling in Montana and rain falling in Pennsylvania may eventually meet in the same river, hundreds of miles from where either drop first touched the ground. Watersheds are invisible boundaries, quietly connecting distant, unrelated places through the simple, patient logic of water always flowing downhill. Groundwater takes centuries to move. While a river might carry a drop of water from mountain to sea in a matter of weeks, groundwater moves far more slowly, sometimes shockingly so. In dense clay or fine-grained rock, groundwater can move only a few inches each year. This means that water entering an aquifer today may not reach a well or spring until centuries from now, long after those who drew it from the sky through rain have been forgotten. This slow pace is part of why aquifers are so vulnerable to overuse. Water pumped out today, especially from deep and ancient reserves, may not be replaced for generations, a reminder that not all water moves at the same patient, hurried pace. Some rivers reverse their flow. In certain coastal rivers, a phenomenon called a tidal bore occurs when a powerful incoming tide pushes against the river's natural downstream flow, sometimes reversing the direction of the water entirely for a period of time. The Qiantang River in China is famous for producing some of the largest tidal bores in the world, walls of water several feet high that surge upstream, drawing crowds who gather each year to watch the river seemingly run backward. These reversals are temporary, lasting only as long as the tide's strength holds, but they offer a striking reminder that even a river's steady, seemingly permanent flow can be gently persuaded, for a while, to change its mind. Water may have come from comets and asteroids. One of the enduring mysteries of Earth's history is where all its water actually came from. Some scientists believe much of it arrived early in the planet's formation, embedded within the very rocks and dust that came together to form Earth. Others believe a significant portion arrived later, delivered by comets and water-rich asteroids that struck the planet during its early, chaotic history. Recent studies of comet ice suggest the ratio of certain elements doesn't always match Earth's oceans perfectly, leaving the exact origin still debated. Whatever the true answer, it means that the rain falling gently outside your window tonight may be, in some very real sense, a visitor from far beyond our own planet. Rainbows are rain and light in conversation. A rainbow forms when sunlight enters a raindrop, slows down and bends, splitting into its full spectrum of colors before reflecting off the inside of the drop and bending again as it exits. Because this precise combination of bending and reflecting only happens at certain angles, each person actually sees a slightly different rainbow, made from an entirely different set of raindrops than the person standing beside them. A rainbow, in other words, is not a fixed object in the sky at all. It is a private, personal conversation between falling rain and traveling light, recreated fresh and slightly differently for every single person who happens to look up at the right moment. Permafrost locks water in frozen ground. Across vast stretches of the Arctic, water exists not as rivers or lakes, but as permafrost, ground that remains frozen solid for 2 or more consecutive years, sometimes for tens of thousands of years. Trapped within this frozen soil is an enormous quantity of ancient water, along with the preserved remains of plants and animals from ice ages long past. As global temperatures shift, some of this permafrost has begun to thaw, releasing water and occasionally revealing remarkably preserved creatures that have rested, frozen and silent, for millennia. Beneath the frozen surface of the far north lies a slow, cold library of ancient water, waiting patiently in the dark. Confluences are where 2 rivers become one. A confluence, the point where 2 rivers meet and merge into a single flow, is often marked by a striking visual difference, especially when the 2 rivers carry different colors of water. Where the pale, silty Missouri River meets the darker waters of the Mississippi, or where the clear blue Rhone meets the murky Arve near Geneva, the 2 currents can remain visibly distinct for a surprising distance downstream before finally blending completely. These confluences are quiet reminders that even after merging, water carries its history with it for a while, a lingering trace of where it came from, slowly fading as it becomes part of something larger. The hydrologic cycle powers weather worldwide. The endless movement of water between ocean, sky, and land does more than simply create rain. It is the engine behind much of the planet's weather. As water evaporates from warm oceans, it carries heat energy upward into the atmosphere. When that vapor condenses into clouds and falls as rain, it releases that stored heat, powering storms, driving wind patterns, and shaping the climate of entire regions. Hurricanes, monsoons, and even the gentle breezes of an ordinary afternoon are all, in some part, expressions of water's constant, restless movement between its many forms, a quiet engine running ceaselessly beneath the surface of everyday weather. Some rivers vanish into deserts. Not every river reaches the sea. In dry, low-lying regions with no outlet to the ocean, rivers instead flow into what are called endorheic basins, closed systems where water simply evaporates or seeps into the ground rather than continuing onward. The Okavango River in southern Africa flows for hundreds of miles only to disappear into the sands of the Kalahari Desert, forming a lush, temporary delta that supports extraordinary wildlife before vanishing entirely. These vanishing rivers are not failures of the water cycle, but simply another of its many endings, proof that a river's journey doesn't always require reaching the sea to be complete. Coral reefs depend on the balance of fresh and salt water. Coral reefs thrive in a delicate balance of salinity, temperature, and clarity, all of which can be disrupted by the nearby presence of fresh water. Too much river runoff can lower salinity and cloud the water with sediment, smothering the delicate coral polyps beneath a fine layer of silt. Yet many of the world's most vibrant reef systems exist near river mouths, benefiting from the nutrients those rivers carry, so long as the balance remains gentle and undisturbed. This fragile relationship between river and reef is a quiet reminder that even the ocean's most colorful, resilient ecosystems remain closely tied to the rhythm of fresh water arriving, patiently, from the land. Rain shapes mountains over millions of years. Mountains may seem eternal and unchanging, but rain is constantly working against them, seeping into cracks, freezing and expanding, and slowly breaking stone apart. Over millions of years, this process, combined with the steady work of rivers and glaciers, can wear down even the tallest peaks. The Appalachian Mountains, once as tall as the Himalayas are today, have been worn down by hundreds of millions of years of rain and erosion into the smoother, gentler ranges we see now. Even the hardest stone is, in the end, no match for the patience of falling water, given enough time and enough rain. The driest place on Earth still sees rain, rarely. The Atacama Desert in Chile, often cited as the driest non-polar place on Earth, has some regions that may go decades without measurable rainfall. And yet, even here, rain does occasionally fall, sometimes triggering a rare and spectacular event known as a desert bloom, in which dormant seeds that have waited patiently in the dry soil for years suddenly burst into flower, transforming the barren landscape into a brief, vivid carpet of color. Within days or weeks, the bloom fades and the desert returns to its quiet stillness, but the seeds remain, buried and waiting once more, prepared to wait however long it takes for the rain to return. Fog is a cloud that touches the ground. There is no real difference between fog and a cloud except elevation. Fog forms when air near the surface cools enough for water vapor to condense into tiny suspended droplets, exactly as it would high in the sky, except here it settles gently around trees, over fields, and along quiet roads. Coastal fog often forms when warm, moist air passes over cold ocean currents, cooling suddenly and dropping close to the water's surface before drifting inland. San Francisco's famous fog, locals sometimes call it Carl, forms this way, rolling in from the cold Pacific and settling over the hills like a cloud that simply forgot to stay in the sky. Dew forms from invisible water vapor. On clear, calm nights, the ground and everything resting upon it can cool rapidly, radiating heat upward into the open sky. As surfaces like grass and leaves cool below the surrounding air's dew point, invisible water vapor in the air condenses directly onto them, forming the small, glistening droplets we see at dawn. Dew requires no rain at all. It is simply water vapor, always present in the air around us, quietly settling out of the atmosphere overnight, appearing each morning as if from nowhere, a soft and temporary gift left behind by the cooling, patient dark. Springs are windows into the underground world. A spring occurs wherever groundwater naturally reaches the surface, often at the base of a hill or along a fracture in bedrock where an aquifer intersects the open air. Some springs release water that has been traveling underground for decades or centuries, filtered slowly through layers of rock and soil along the way. Hot springs, warmed by contact with deep geothermal heat, bring water to the surface that may have originated as rain that fell long before it ever touched magma-warmed stone. Every spring is, in a small way, a window, a brief glimpse into the slow, hidden rivers moving quietly beneath the ground. Oxbow lakes are abandoned river bends. As a meandering river's curves grow more pronounced over time, the narrow neck of land separating two bends can eventually erode away entirely, allowing the river to cut a new, straighter path. The old curved section is left behind, cut off from the main channel, forming a crescent-shaped body of still water called an oxbow lake. No longer fed by the river's current, these lakes slowly fill with sediment and vegetation over the following decades, gradually transforming into marshland and eventually disappearing altogether. An oxbow lake is, in essence, a river's memory, a quiet, curved trace of a path the water no longer takes. The Amazon rainforest recycles its rain many times. As mentioned before, the vast canopy of the Amazon releases enormous amounts of water vapor through the leaves of its billions of trees. This vapor rises, cools, and falls again as rain, sometimes landing hundreds of miles from where it evaporated, only to be drawn upward once more by the next stretch of forest it passes over. Some water molecules may complete this cycle 5 or 6 times before finally reaching a river and continuing on toward the Atlantic Ocean. In this way, the rainforest does not simply depend on rain. It actively participates in creating it, breathing moisture skyward again and again in a long, looping conversation between forest and cloud. Rivers carry sediment that built entire landmasses. Over millions of years, the sediment carried by rivers has done more than simply build small deltas. It has constructed entire regions of land. Much of the Mississippi Delta, the Nile Delta, and the vast plains of Bangladesh at the mouth of the Ganges and Brahmaputra rivers were built, grain by grain, from sediment worn away from distant mountains, and carried patiently downstream over unimaginable spans of time. These landscapes are, in the truest sense, gifts from rivers, entire regions of fertile, livable land constructed slowly from the quiet, ongoing erosion of mountains that may lie thousands of miles away. Water memory in ice cores tells climate history. Deep within glaciers and polar ice sheets, layers of compacted snow preserve a remarkably detailed record of the planet's past climate, sometimes stretching back hundreds of thousands of years. Scientists extract long cylinders of this ancient ice, called ice cores, and study tiny bubbles of trapped air, along with the chemical composition of the ice itself, to reconstruct ancient temperatures, atmospheric conditions, and even volcanic eruptions from the deep past. Each layer represents a single year, or sometimes a single season, a frozen diary written in ice, patiently keeping a record that no other archive on Earth could have preserved so precisely. Tributaries feed the growth of larger rivers. No great river flows alone. Every major river is fed by a network of smaller tributaries, streams and smaller rivers that join together, gradually combining their flow into something far larger than any single one of them could achieve alone. The Amazon River, for instance, is fed by over 1,000 tributaries, some of which are themselves large enough to rank among the world's major rivers if they existed independently. This gradual gathering of smaller flows into one immense current is a quiet reminder that even the mightiest rivers begin as a patient collaboration between countless smaller, humbler streams. Waterways were the first highways of civilization. Long before roads or railways connected distant communities, rivers served as the primary means of travel and trade. Boats could carry goods and people far more efficiently along a river's current than any traveler could manage on foot across rough terrain. Ancient trade routes along the Nile, the Tigris and Euphrates, and the Yangtze allowed distant cultures to exchange ideas, goods, and technology centuries before overland routes were fully developed. In many ways, rivers were the original highways of human history, quiet ribbons of water that carried not just cargo, but the slow, steady spread of civilization itself. The Mississippi watershed spans much of a continent. The Mississippi River and its many tributaries drain water from an enormous portion of the central United States, an area covering roughly 40% of the continental country. Rain falling on a farm in Montana, snowmelt trickling down a hillside in Pennsylvania, and a summer storm passing over Louisiana may all eventually find their way into the same vast river system, converging slowly over thousands of miles before finally reaching the Gulf of Mexico. This immense, interconnected watershed is a quiet reminder of just how deeply linked distant, unrelated places can be, joined together by nothing more than the simple, patient logic of water flowing downhill. Braided rivers split and rejoin over gravel plains. In certain landscapes, particularly those with an abundance of loose sediment and a steep gradient, rivers don't flow in a single channel at all. Instead, they split into multiple shifting strands that weave around gravel bars, only to rejoin and split again farther downstream, forming a braided pattern when viewed from above. These braided rivers, common near glacier-fed mountain streams, constantly shift their many channels, sometimes reshaping their pattern significantly after a single large flood. A braided river never settles into a fixed form. It exists instead in a permanent, gentle state of change, always dividing, always reuniting. Every river eventually reaches base level. In hydrology, base level refers to the lowest point to which a river can erode its channel, usually determined by the elevation of the body of water it eventually flows into. For most rivers, this base level is the ocean itself. As a river approaches its base level, its ability to erode the landscape diminishes, and the river instead begins to deposit the sediment it has carried for its entire journey. This is why river valleys tend to widen and flatten as they near the sea, the water slowing, softening, and finally settling into the wide, patient calm that comes just before a long journey's end. Rain gauges have a surprisingly long history. Humans have been measuring rainfall for thousands of years, motivated largely by the need to track water for agriculture. Ancient records from Korea describe standardized rain gauges used as early as the 15th century, allowing officials to compare rainfall across different regions and years. In ancient India, rainfall measurements were used to help estimate crop yields and set fair taxation. These early efforts to measure something as simple as rain reflect a very old and very human desire to understand water, to bring a small measure of predictability to something that has always remained, in the end, gently beyond our full control. Cloud seeding is a human attempt to trigger rain. In some regions facing drought, scientists have experimented with cloud seeding, a technique that involves introducing tiny particles, often silver iodide, into clouds to encourage water droplets to form and grow large enough to fall as rain. The results are often modest and difficult to measure precisely, since it's hard to know how much rain would have fallen anyway. Still, several countries continue to invest in cloud seeding programs, hoping to coax a little more rain from clouds that might otherwise pass by without releasing their moisture. It is, in its own way, a very old hope, dressed in modern technology, the same wish for rain that farmers have carried for thousands of years. Ancient aqueducts moved water across empires. Long before modern plumbing, ancient civilizations built extraordinary systems to transport water across great distances. Roman aqueducts, some stretching over 50 miles, used a very slight, carefully calculated downward slope to carry water entirely by gravity from distant mountain springs into the heart of bustling cities. Some of these structures were so well engineered that portions remain standing, and in rare cases still functioning, nearly 2,000 years later. These ancient channels represent one of humanity's earliest and most impressive attempts to guide water's natural, downward journey toward a destination of our own choosing. Hidden rivers flow under cities. Many modern cities were built atop older streams and small rivers that have since been covered over, redirected into underground pipes to make way for streets and buildings. The Fleet River once ran openly through London before being gradually buried beneath the growing city, and it still flows today, unseen, through underground culverts beneath busy streets. Similar buried rivers exist beneath New York City, Toronto, and countless other urban centers. Somewhere beneath the noise and motion of a modern city, an old, forgotten river may still be flowing quietly through the dark, carrying on a journey that predates every building above it. Salt marshes filter water before it reaches the sea. Along many coastlines, wide expanses of salt marsh grass grow in the shifting zone between land and sea, flooded regularly by the tides. As water moves slowly through these dense grasses, sediment settles out, excess nutrients are absorbed, and pollutants are gradually broken down before the water continues on toward the open ocean. Salt marshes also act as a buffer against storm surges, absorbing the force of incoming waves and protecting the land behind them. Quiet and often overlooked, these marshes perform an essential, ongoing service, patiently cleaning and softening the boundary between river and sea. Underground caves are carved by water over eons. Many of the world's most spectacular cave systems were formed not by any dramatic event, but by the slow, patient work of slightly acidic water dissolving limestone bedrock over hundreds of thousands of years. As rainwater seeps through soil, it picks up carbon dioxide, becoming just acidic enough to slowly dissolve certain types of rock as it trickles downward. Over time, this process hollows out enormous underground chambers, connected by narrow passages and decorated with mineral formations built from the same patient process. Mammoth Cave in Kentucky, the longest known cave system in the world, continues to grow even today, carved slowly by water that has been at work for a very long time. Stalactites and stalagmites are slow water sculptures. Within limestone caves, water dripping from the ceiling carries dissolved minerals, primarily calcium carbonate, which are slowly deposited as the water evaporates, leaving behind delicate mineral formations. Stalactites grow downward from cave ceilings, while stalagmites build upward from the cave floor beneath them, sometimes eventually meeting to form a solid column. These formations grow at an astonishingly slow pace, often less than 1/10 of an inch per century, meaning even a modest stalactite may represent tens of thousands of years of patient, mineral-laden dripping, a sculpture built by water working far more slowly than almost anything else in nature. Some raindrops never reach the ground. On very hot, dry days, rain falling from a cloud can sometimes evaporate completely before it ever touches the earth, a phenomenon known as virga. From a distance, virga appears as soft, wispy streaks trailing beneath a cloud, like a curtain of rain hanging in the sky, and yet the ground below remains completely dry. This happens often in desert regions, where the air near the surface is so dry and warm that falling raindrops simply cannot survive the descent. Virga is a quiet reminder that not every journey water begins is one it manages to finish, some drops returning to vapor before they ever complete their fall. Rivers freeze from the top down. When temperatures drop low enough, a river's surface begins to freeze first, forming a layer of ice that gradually thickens while the water beneath continues to flow, insulated from the coldest air above by the ice itself. This is why fish and other aquatic life can survive beneath a frozen river through even the harshest winters, sheltered in liquid water even as the surface above hardens into solid ice. In very cold, fast-moving sections, a phenomenon called phrasal ice can form, tiny ice crystals suspended directly within the moving water itself, sometimes clumping together to create slushy, floating masses long before a solid surface ever forms. Lakes turn over seasonally, mixing their water. Many lakes in temperate climates undergo a process called turnover, occurring in spring and fall, when the temperature of the surface water matches the temperature of the deeper water, allowing the entire lake to mix from top to bottom. During summer and winter, lakes typically settle into distinct layers, with warmer or cooler water resting at different depths depending on the season. Turnover redistributes oxygen and nutrients throughout the lake, refreshing conditions for the fish and organisms living within it. This seasonal mixing is a quiet, twice-yearly reset, an entire lake gently stirring itself back into balance as the seasons change around it. The longest river debate continues between the Nile and the Amazon. For many years, textbooks confidently listed the Nile as the world's longest river, stretching over 4,000 miles through northeastern Africa. But more recent surveys, using satellite measurements to trace the Amazon's most distant tributary sources deep in the Andes, suggest the Amazon may actually be slightly longer, depending on exactly which small tributary is counted as its true beginning. The debate remains unresolved, a reminder that even something as seemingly simple as measuring a river's length depends heavily on decisions about where, precisely, a river's story is considered to begin. Rivers often serve as borders and boundaries. Throughout history, rivers have frequently defined the boundaries between nations, states, and territories, their fixed, visible presence offering a convenient and easily recognized line of separation. The Rio Grande divides the United States and Mexico. The Danube has, at various points in history, marked the edge of empires. Yet because rivers naturally shift their course over time, these borders have occasionally become a source of dispute, as a river slowly meanders away from the line originally agreed upon by mapmakers. A river, patient and ever-changing, makes an uneasy boundary, always drifting gently away from whatever fixed line humans try to draw upon it. The deep sea receives no rain, and yet water still arrives. Far beneath the ocean's surface, sunlight never reaches, and rain, of course, never falls directly into these depths in any way distinct from the surrounding seawater. and yet fresh water still finds its way down, carried by sinking currents formed when cold, salty water near the polar regions becomes dense enough to plunge toward the ocean floor, driving a slow, global circulation system that carries oxygen and nutrients to the deepest parts of the sea. This vast, invisible current, sometimes called the ocean conveyor belt, can take 1,000 years or more to complete a single full circuit around the planet's oceans. Underwater rivers and waterfalls exist within the ocean. In certain places, differences in salinity, temperature, and density between layers of ocean water create currents so distinct that they behave like rivers flowing within the sea itself, complete with visible boundaries and even underwater waterfalls. Off the coast of Denmark, near the straits separating the Baltic and North Seas, dense, cold water plunges downward in what is sometimes called the world's largest underwater waterfall, though it remains completely invisible from the surface. These hidden currents move enormous volumes of water, silent and unseen, coursing through the ocean's depths in patterns as complex and purposeful as any river on land. Every raindrop's journey is unique, yet endlessly reused. Though water itself is never truly created or destroyed, no two raindrops ever follow quite the same path through the water cycle. One drop might evaporate from a warm tropical sea, drift for days as vapor, and fall as snow atop a distant mountain, resting there for years before finally melting into a mountain stream. Another might rise from a puddle after an afternoon shower and fall again as rain the very same evening, barely a few miles from where it started. Though the water itself is ancient, recycled endlessly through countless forms, each individual journey remains, in its own quiet way, entirely its own. The largest river by volume is not the longest. While the Nile and Amazon compete for the title of longest river, the Amazon holds an uncontested record for volume, discharging more water into the ocean than the next several largest rivers in the world combined. In fact, the Amazon alone accounts for roughly 1/5 of all the fresh water that flows from rivers into the world's oceans. Standing at certain points along its banks, it can be difficult to see the opposite shore at all, the river resembling something closer to a slow, brown sea than what most people imagine when they picture a river winding through a forest. Water has a memory of temperature written into its structure. Though it may sound poetic rather than scientific, water genuinely does carry a kind of physical memory of the conditions under which it formed. The specific isotopes of oxygen and hydrogen present in a sample of water shift slightly depending on the temperature at the time it evaporated and condensed. By studying these subtle isotopic signatures in ancient ice cores, ocean sediments, and cave formations, scientists can reconstruct temperatures from thousands, even hundreds of thousands of years in the past. In this way, water quietly records its own history, preserving a faint, chemical echo of the climate it was born into, long after that climate itself has changed. The Ganges is considered sacred by hundreds of millions. Few rivers hold as much cultural and spiritual significance as the Ganges, revered in Hinduism as a goddess and considered capable of washing away sins and purifying the soul. Millions of pilgrims travel to its banks each year to bathe in its waters, and its role extends far beyond religion into daily life, providing water for drinking, farming, and countless communities along its nearly 1,500-mile course from the Himalayas to the Bay of Bengal. The reverence shown toward the Ganges reflects something deeply and widely human, a recognition, expressed differently across cultures throughout history, of just how central rivers are to the very possibility of life. The water cycle connects the highest peaks to the deepest trenches. From the summit of Mount Everest, where snow rests just below the edge of space, to the crushing darkness of the Mariana Trench nearly 7 miles beneath the ocean's surface, water moves in a single, unbroken cycle connecting the very highest and lowest points on the planet. Snow melts on mountain peaks, feeds rivers that carve their way to the sea, mixes into currents that circulate through the deep ocean, and eventually rises again as vapor to begin the journey anew. There is no true beginning and no true end to this cycle, only a slow, patient, endlessly repeating circuit binding together every extreme corner of the earth. Icicles form as dripping water refreezes layer by layer. When snow or ice on a roof melts slightly during the day and then refreezes as temperatures drop at night, the process can repeat night after night, each new layer of frozen water adding to the icicle's length. Because the water drips and freezes gradually, icicles often form in slightly irregular, ribbed patterns, each ridge a faint record of a single freeze-thaw cycle. In very cold, dry conditions, icicles can grow remarkably long, sometimes stretching several feet from the eaves of a building, a quiet, frozen record of many small showers of melting and freezing water, repeated patiently over the course of an entire winter. Rain shadows create deserts beside mountains. When moist air is forced to rise over a mountain range, it cools and releases much of its moisture as rain or snow on the windward side. By the time that same air descends on the far side of the mountains, it has lost most of its moisture, creating a dry region known as a rain shadow. This effect explains why deserts like the Mojave exist relatively close to wetter coastal regions, separated only by a mountain range that intercepts nearly all the incoming moisture before it can travel any farther inland. A rain shadow is a quiet demonstration of just how much difference a single mountain range can make in a landscape's relationship with water. The ocean salt comes largely from rivers. It might seem strange that rivers, which carry fresh water, are one of the primary sources of the ocean's salt. As rain falls and flows across the land, it slowly dissolves tiny amounts of minerals from rocks and soil, carrying these dissolved salts along with it toward the sea. While any single river's water tastes fresh, over hundreds of millions of years, this slow, continuous delivery of dissolved minerals has gradually built up the ocean's salinity to the levels we know today. In a very real sense, the saltiness of the sea is the patient, accumulated legacy of countless rivers, each carrying a small, invisible cargo of dissolved stone. Freshwater makes up a surprisingly small share of Earth's total water. Though rivers, lakes, and rainfall are what most people picture when they think of water, fresh water actually accounts for only about 3% of all the water on Earth. Of that small fraction, roughly 2/3 is locked away in glaciers and polar ice caps, leaving only a sliver available as liquid fresh water in rivers, lakes, and accessible groundwater. This means that the vast majority of water most living things depend upon for survival makes up only a tiny fraction of the planet's total water. A small, precious portion carefully cycling through clouds and rivers while the rest rests, mostly untouched, in ocean and ice. The sound of rain has a physical explanation. The gentle, steady sound of rain falling comes from thousands of tiny impacts, each raindrop striking a surface and briefly compressing the air around it, along with any trapped air bubbles beneath the water's surface if it lands in a puddle or body of water. Interestingly, much of the sound produced by rain falling on water actually comes not from the initial splash, but from tiny air bubbles trapped just beneath the surface, vibrating briefly before rising and bursting. This is part of why rain sounds so different falling on grass, pavement, or a rooftop, each surface interacting with the same falling water in its own distinct acoustic way. The Yangtze River carries a nation's history within it. Stretching nearly 4,000 miles across China, the Yangtze has shaped Chinese civilization for thousands of years, serving as both a vital trade route and, at times, an unpredictable source of devastating floods. The Three Gorges Dam, built along its course, is the largest hydroelectric structure in the world, transforming a stretch of the river into a vast reservoir while also controlling floods that once claimed countless lives throughout the region's long history. The Yangtze, like so many of the world's great rivers, is not simply a body of water. It is a thread running through centuries of human memory, joy, and hardship alike. Rivers can run in colors rarely expected, like pink or red. In rare cases, rivers take on strikingly unusual colors due to specific mineral content, algae, or bacteria thriving within them. The Rio Tinto in Spain runs a deep, rust-red color due to high concentrations of iron and other minerals dissolved from the surrounding mining region, a hue so distinctive that scientists have studied its unusual chemistry as a possible analog for ancient rivers that may once have flowed on Mars. Elsewhere, certain algae blooms can tint rivers and lakes shades of pink or green for a season, before fading again as conditions change. A fleeting, colorful reminder of just how many small factors quietly shape the appearance of moving water. Waves carry the memory of distant storms. Ocean waves that reach a peaceful, sunny beach may have originated from a storm thousands of miles away, days earlier. As wind blows across the open ocean, it transfers energy into the water, creating waves that can travel enormous distances after the storm that generated them has long since passed. This is why calm, glassy days at the beach can sometimes still bring in a set of surprisingly large waves, distant echoes of turbulent weather occurring somewhere far out at sea, arriving gently, days later, upon a shore that never even felt the storm itself. Tides are shaped by the gentle pull of the moon and sun. Twice each day, in most coastal regions, the ocean rises and falls in a rhythm dictated largely by the gravitational pull of the moon, with a smaller but still meaningful contribution from the sun. As the moon orbits the Earth, its gravity tugs gently on the ocean, creating a slight bulge of water on the side of the planet facing it, along with a corresponding bulge on the opposite side. As the Earth rotates beneath these bulges, coastlines experience the rise and fall we call the tide, a slow, patient rhythm connecting the ocean's movement to the quiet, distant presence of the moon overhead. Spring tides and neap tides depend on the alignment of sun and moon. When the sun, moon, and Earth align during a new or full moon, their combined gravitational pull produces especially strong tides, known as spring tides, regardless of the actual season. When the sun and moon are positioned at right angles relative to Earth, their gravitational effects partially cancel each other out, producing gentler neap tides. This monthly rhythm, shifting steadily between stronger and weaker tides, plays out along every coastline on Earth, a quiet celestial choreography that has guided fishing, navigation, and coastal life for as long as people have lived near the sea. The Yellow River earned its name and its history from sediment. Known in Chinese as Huanghe, the Yellow River carries an extraordinary amount of fine, yellow-brown silt eroded from the Les Plateau upstream, giving the water its distinctive color and its name. This heavy sediment load has historically caused the riverbed to rise over time as silt settles, sometimes lifting the river's course above the surrounding land and requiring massive levees to contain it. When these levees have failed throughout history, the resulting floods have been among the deadliest in recorded history, earning the river the somber nickname China's Sorrow, a powerful reminder of both the life-giving and destructive power that a single great river can hold. Karst landscapes reveal water's slow sculpting work. In regions built upon limestone bedrock, centuries of slightly acidic rainwater dissolve the rock from within, creating a distinctive landscape known as karst, characterized by sinkholes, underground caves, disappearing streams, and dramatic natural towers of stone. Southern China's Guilin region, famous for its otherworldly limestone peaks rising from the mist, is one of the most striking examples of karst topography on Earth, an entire landscape shaped almost entirely by water's patient, dissolving touch, working invisibly for millions of years beneath what was once a much flatter surface. The polar ice caps hold enough water to reshape coastlines. Locked within the ice sheets of Antarctica and Greenland is an enormous quantity of fresh water, so much that if it were to melt entirely, global sea levels would rise by well over 200 feet, submerging coastal cities around the world. This ice has been accumulating for hundreds of thousands of years, compacted layer upon layer from ancient snowfall, and it moves, however slowly, constantly flowing outward toward the sea in massive, grinding glaciers. The ice caps stand as some of the largest and most patient reservoirs of fresh water on the planet, silent, immense, and steadily on the move. Mangrove forests protect coastlines using tangled roots and tidal water. Along many tropical coastlines, mangrove trees grow directly in salty, shifting tidal waters, their tangled root systems trapping sediment and gradually building up the land around them. These unique forests serve as a buffer between land and sea, absorbing the force of storm surges and providing shelter for countless fish, birds, and other wildlife within their flooded, root-tangled understory. Mangroves thrive precisely because they have adapted to a challenging, ever-changing relationship with water, rising and falling twice daily with the tide, patient and resilient within a landscape few other trees could ever tolerate. Rain in the desert can trigger flash floods far from any storm. In arid regions, a storm many miles away can send a sudden surge of water rushing through a dry riverbed, or wash, that appeared to have seen no rain at all. Because desert soil is often compacted and unable to absorb water quickly, even a modest rainfall upstream can result in a fast-moving flash flood downstream, arriving with little warning under otherwise clear skies. These sudden floods have shaped desert canyons over thousands of years, carving narrow, twisting slot canyons through solid rock, evidence of water's power even in landscapes where it seems, most days, entirely absent. The Colorado River no longer reaches the sea most years. Once flowing all the way to the Gulf of California, the Colorado River has been so extensively used for irrigation and drinking water across the American Southwest that in most recent years, it no longer reaches the ocean at all, drying up instead within its own delta, miles short of the sea it once fed. This dramatic change highlights the delicate balance between human need and the natural rhythm of a river's journey, a reminder that even one of the most iconic rivers in North America can, under enough pressure, quietly fail to complete the very journey that has defined it for millions of years. Water striders walk atop the surface tension of ponds and streams. Among the many small dramas that unfold on the surface of calm, quiet water are water striders, insects that use the water's own surface tension to walk across ponds and slow-moving streams without ever breaking through. Their legs are coated with tiny, water-repellent hairs that trap a thin layer of air, allowing them to distribute their weight so effectively that the surface simply dimples slightly beneath them rather than giving way. It is a small, easily overlooked example of just how much complexity and quiet wonder exists atop even the stillest, most ordinary puddle or pond. Hot springs form where groundwater meets deep, hidden heat. In geologically active regions, groundwater can seep down far enough to come into contact with magma or extremely hot rock deep underground, heating the water before it rises back to the surface as a hot spring or geyser. Yellowstone National Park sits atop one of the largest active volcanic systems in the world, feeding thousands of hydrothermal features, including Old Faithful, a geyser that has erupted with remarkable, though not perfectly exact, regularity for well over a century. These hot springs are a striking reminder that water's long journey can sometimes lead it, briefly, into direct contact with the fiery heart of the Earth itself, before rising once more to the surface. The Ob River in Siberia freezes for months at a time. In the far north of Russia, the Ob River, one of the longest rivers in the world, remains frozen solid for much of the year, its surface hard enough to support the weight of vehicles during the coldest months. When spring finally arrives and the ice begins to break apart, the resulting ice jams can cause severe flooding, as chunks of thick river ice pile up and temporarily block the flow of water downstream. This dramatic seasonal cycle, freezing solid for half the year only to break violently free each spring, reflects just how differently a river can behave depending on the climate it flows through. Icebergs are mostly hidden beneath the water's surface. The familiar phrase describing only the tip of the iceberg comes from simple physics. Ice is only slightly less dense than seawater, meaning that roughly 90% of an iceberg's total mass remains submerged, hidden beneath the surface where it cannot easily be seen. This hidden bulk is precisely what made icebergs so dangerous to ships throughout history, their true size and shape concealed beneath the waterline, invisible until a vessel had already drawn dangerously close. An iceberg, drifting slowly and silently through cold ocean waters, carries far more of itself in secret than it ever reveals above the surface. Water wheels harness the power of moving rivers for centuries. Long before electricity, communities built water wheels along rivers and streams to harness the constant motion of flowing water, grinding grain into flour, powering early textile mills, and even pumping water uphill to irrigate distant fields. These simple, effective machines converted the steady, patient force of moving water into mechanical energy, allowing small communities to accomplish tasks that would otherwise have required enormous manual labor. In many ways, water wheels represent one of humanity's earliest and most elegant partnerships with the natural water cycle, quietly borrowing a fraction of a river's endless motion for practical, everyday use. The Danube flows through more countries than any other river. Winding nearly 1,800 miles across Central and Eastern Europe, the Danube passes through or borders 10 different countries, more than any other river in the world. Along its banks, it has witnessed the rise and fall of empires, served as a vital trade route since ancient times, and continues today to connect cities as varied as Vienna, Budapest, and Belgrade. Its long, international course is a quiet reminder that rivers rarely respect the borders humans draw upon a map, flowing instead according to the much older, much simpler logic of gravity and gradient, indifferent to the shifting lines of nations. Permeable soil determines how quickly rain becomes groundwater. Not all rain follows the same path once it reaches the ground. Sandy, loose soil allows water to seep downward quickly, replenishing groundwater within days or weeks. Dense clay soils, on the other hand, resist infiltration, causing more water to run off along the surface, feeding streams and rivers rather than sinking underground. Urban areas, covered extensively in pavement and concrete, prevent infiltration almost entirely, sending the vast majority of rainfall directly into storm drains rather than allowing it to replenish the aquifers below. The type of ground beneath a raindrop, more than almost anything else, quietly determines where that drop's journey will lead next. The Congo River is the deepest river in the world. Flowing through the dense rainforest of Central Africa, the Congo River reaches depths of over 700 feet in certain sections, making it the deepest river known anywhere on Earth. This extraordinary depth, combined with powerful currents and numerous rapids, has made portions of the Congo notoriously difficult to navigate, and even today, only partially explored by scientists studying the unique fish species that have evolved within its dark, fast-moving depths. The Congo is also unusual in that it crosses the equator twice along its course, feeding it a steady, year-round supply of rain from alternating hemispheres. Some fish can survive being frozen and thaw again. In certain extremely cold environments, some fish species have evolved remarkable adaptations to survive partial freezing, producing natural antifreeze proteins that prevent ice crystals from forming within their cells even as the water around them solidifies. While complete freezing remains fatal for nearly all fish, some can tolerate ice forming in the spaces between their cells, entering a state of suspended animation until warmer temperatures return. This remarkable resilience reflects just how deeply life has adapted to water's many forms, evolving alongside the seasonal, sometimes dramatic transformations that rivers and lakes undergo throughout a single year. The Aral Sea shows what happens when rivers are diverted. Once one of the largest lakes in the world, the Aral Sea in Central Asia has shrunk dramatically since the mid-20th century, after the rivers that fed it were diverted extensively for agricultural irrigation. What remains today is a small fraction of its original size, leaving behind vast stretches of exposed, salt-crusted seabed and stranded fishing boats resting in what is now dry desert, miles from any remaining water. The story of the Aral Sea stands as a sobering reminder of how quickly a body of water, even one that seems permanent and immense, can vanish when the rivers that sustain it are redirected elsewhere. Rain in the tropics often follows a strict daily rhythm. In many tropical regions, rainfall follows a remarkably consistent daily pattern, with clear mornings giving way to towering afternoon thunderstorms as the sun heats the ground and moist air rises rapidly into the atmosphere. This predictable rhythm has shaped daily life for communities throughout the tropics for generations, with markets, fieldwork, and travel often planned carefully around the near certainty of an afternoon downpour. Unlike the more scattered, unpredictable rain of temperate climates, tropical rainfall often arrives with a dependable regularity, a daily appointment kept faithfully by the sky, hour after hour, season after season. The Ganges and Brahmaputra together form one of the largest deltas on Earth. Where the Ganges and Brahmaputra rivers converge near the Bay of Bengal, they create the Sundarbans, the largest river delta in the world, a vast, low-lying region of mangrove forests, shifting channels, and fertile farmland spanning parts of India and Bangladesh. This immense delta is built entirely from sediment carried down from the Himalayas, deposited patiently over thousands of years as the two great rivers flow and spread near the sea. It remains one of the most biologically rich and most vulnerable landscapes on the planet, a place where the ongoing story of water and land continues to be written daily by the rivers themselves. Lightning is closely tied to the formation of rain. Within a developing thunderstorm, rising and falling currents of air cause ice particles and water droplets to collide repeatedly, building up static electrical charge within the cloud. When this charge becomes strong enough, it discharges suddenly as lightning, heating the surrounding air so rapidly that it produces the shock wave we hear as thunder. This same turbulent motion within a storm cloud, the very process that generates lightning, is also what allows water droplets to grow large enough to fall as rain. In this way, the flash and the downpour are close companions, both born from the same restless motion occurring within a single storm. The Mekong River sustains millions across Southeast Asia. Flowing through China, Myanmar, Laos, Thailand, Cambodia, and Vietnam, the Mekong River supports one of the most productive inland fisheries in the world, providing food and livelihood for tens of millions of people across the region. Its annual flood cycle, driven by seasonal monsoon rains, replenishes Cambodia's Tonle Sap Lake, causing it to expand dramatically in size each year before receding again as the dry season returns. This rhythm, an entire lake breathing in and out with the rain, has shaped the culture, agriculture, and daily rhythms of communities along the Mekong for countless generations. The driest inhabited continent still depends entirely on rare rainfall. Australia, the driest inhabited continent on Earth, has developed an intricate relationship with its unpredictable rainfall, with vast stretches of the outback sometimes going years between significant rain events. Many Australian rivers are described as ephemeral, flowing only after rare storms and remaining dry for the rest of the year, their sandy beds serving as roads and pathways until the next rare downpour arrives, transforming them once again, however briefly, into rushing water. This dramatic, unpredictable relationship with rain has shaped much of Australia's unique plant and animal life, all patiently adapted to wait, sometimes for years, for water's return. Groundwater depletion can cause the ground itself to sink. When groundwater is pumped out of an aquifer faster than it can be naturally replenished, the empty spaces once filled with water can gradually compact under the weight of the overlying soil and rock, causing the ground surface above to sink, a phenomenon known as subsidence. Parts of California's Central Valley have sunk by more than 28 feet over the past century due to extensive groundwater pumping for agriculture, a slow, largely invisible collapse occurring far beneath the surface of everyday life. This quiet sinking is a sobering reminder that water removed from deep, ancient aquifers is not always easily replaced, even by many years of steady rain. Waterspouts are tornadoes that form over open water. Under certain conditions, particularly warm water and unstable air, rotating columns of air can form over lakes or oceans, drawing water upward in a dramatic, spinning funnel known as a waterspout. Though they can appear dramatic and even similar in shape to tornadoes on land, most waterspouts are relatively weak and short-lived. Though they can still pose a danger to boats caught in their path, waterspouts serve as a striking visual reminder of just how much energy can gather within the simple, everyday interaction between warm water and moving air. The Great Lakes hold a significant share of the world's surface fresh water. Together, Lake Superior, Michigan, Huron, Erie, and Ontario contain roughly 1/5 of all the fresh surface water on Earth, an immense reserve formed by the slow retreat of glaciers roughly 10,000 years ago. Lake Superior alone is so large that it could cover the entire surface of the contiguous United States to a depth of about 1 foot if its water were somehow spread evenly across the land. These vast, glacially carved basins represent one of the most significant sources of accessible fresh water on the planet, quietly holding, in a handful of connected lakes, a substantial share of all the liquid fresh water available to life on Earth. Rainfall records reveal some places receive rain almost daily. Mawsynram, a small village in northeastern India, holds the record for the highest average annual rainfall on Earth, receiving well over 400 inches of rain each year, driven by monsoon winds forced upward against the surrounding hills. Residents there have adapted their entire way of life around near-constant rainfall, weaving bridges from living tree roots that grow stronger, rather than weaker, in the damp, humid climate. In a place where rain is less an event than a near-permanent condition, water shapes not just the landscape, but the very architecture and daily rhythm of life itself. Antarctica is technically classified as a desert. Despite holding roughly 70% of the world's fresh water, locked away in its massive ice sheets, Antarctica receives so little actual precipitation. Most of the continent gets less than 2 inches of snow-equivalent moisture each year, that it is technically classified as a desert. The ice that has accumulated there did not arrive quickly. It built up slowly over hundreds of thousands of years, one thin, patient snowfall at a time, each layer compacting beneath the ones that followed until it became the vast, frozen reservoir that exists today. Antarctica is, in this sense, both one of the wettest and one of the driest places on Earth at once. Underground water can be older than the rivers that feed it today. In certain deep, isolated aquifers, scientists have discovered water so old that it fell as rain long before the rivers currently flowing on the surface above even existed in their present form. This ancient groundwater, sometimes called fossil water, has been resting undisturbed for tens of thousands of years, cut off from the modern water cycle, moving only inches at a time through dense rock. When this water is finally drawn to the surface through a well, it represents rainfall from a climate, and sometimes a world, entirely different from the one we know today. The Okavango Delta is a river without an ocean. Rather than flowing into the sea, the Okavango River in southern Africa spreads out into a vast inland delta within the Kalahari Desert, its waters gradually absorbed by sand and evaporated under the sun, rather than reaching any ocean at all. Despite this seemingly abrupt ending, the Okavango Delta becomes, for several months each year, a lush oasis supporting an extraordinary concentration of wildlife in the middle of an otherwise dry landscape. It is one of nature's most striking demonstrations that a river's journey need not end at the sea to leave behind something remarkable. Snowpack acts as a slow-release reservoir for entire regions. In mountainous regions around the world, winter snowfall accumulates gradually into deep snowpack, which then melts slowly throughout the spring and summer, feeding rivers and reservoirs long after the last snowstorm has passed. Much of the American West depends heavily on this slow, seasonal release, with mountain snowpack functioning as a natural reservoir far larger than any dam built by human hands. When snowpack is thin during a particular winter, the effects can ripple through an entire region's water supply for the rest of the year, a quiet reminder that a single season snowfall can shape the availability of water many months later. The Volga is the longest river in Europe, winding over 2,000 miles through Russia before emptying into the Caspian Sea. The Volga has served as a central artery of Russian culture, trade, and history for centuries, celebrated in folk songs, literature, and art. Unlike most major rivers, the Volga does not flow into any ocean at all, instead terminating in the Caspian Sea, the largest inland body of water on Earth, itself a landlocked remnant of a much larger ancient sea that once covered a far greater area many millions of years ago. Raindrop size varies depending on the type of storm. Not all rain falls in drops of the same size. Gentle drizzle consists of very small droplets, often less than half a millimeter across, drifting down slowly and settling almost silently. Heavy thunderstorm rain, by contrast, often falls in much larger drops, sometimes several millimeters wide, driven downward with considerable force and speed. The size of a raindrop depends on the conditions within the cloud that produced it, including the strength of the updrafts holding droplets aloft, and the amount of moisture available for them to grow before finally succumbing to gravity's steady, patient pull. The Zambezi River carries water over one of the largest waterfalls on Earth. Victoria Falls, where the Zambezi River plunges over a mile-wide cliff along the border of Zambia and Zimbabwe, produces a curtain of falling water so immense that the resulting mist can be seen and heard from many miles away, earning it the local name Mocio Atunya, or the smoke that thunders. The falls were carved gradually over millions of years as the river eroded a series of basalt gorges, retreating slowly upstream in much the same way as Niagara Falls, a reminder that even the world's most dramatic waterfalls are, in their own way, simply another chapter in water's endless, patient reshaping of stone. Some clouds produce rain that freezes on contact. Freezing rain occurs when raindrops fall through a thin layer of freezing air near the ground after having formed in a warmer layer higher up, allowing them to remain liquid until the moment they strike a cold surface, where they instantly freeze into a smooth, heavy coating of ice. This delicate balance of temperature layers can coat entire landscapes in a shimmering, treacherous glaze, weighing down power lines and tree branches with astonishing weight. Freezing rain is a striking example of just how sensitive water's behavior can be to even small shifts in temperature along its journey to the ground. Riparian zones along riverbanks support disproportionate biodiversity. The narrow strip of land bordering a river or stream, known as a riparian zone, often supports a remarkable concentration of plant and animal life compared to the surrounding landscape, benefiting from consistent moisture, nutrient-rich soil, and the shelter provided by streamside vegetation. These zones serve as vital corridors for wildlife movement, filter pollutants before they reach the water, and help stabilize riverbanks against erosion. Though often just a thin green ribbon on a map, a healthy riparian zone plays an outsized role in the overall health of the river it borders. The Indus River shaped one of the earliest known urban civilizations. Along the banks of the Indus River, in what is now Pakistan and northwestern India, one of the world's earliest urban civilizations flourished more than 4,000 years ago, building remarkably sophisticated cities with advanced drainage systems and standardized brick construction. The Indus Valley civilization depended heavily on the river's seasonal flooding to fertilize its fields, much like ancient Egypt relied on the Nile. Though the reasons for its eventual decline remain debated among historians, changes in the river's course and rainfall patterns are believed to have played a significant role in reshaping the fate of this ancient society. Permafrost lakes can appear and disappear as ice melts. In parts of the Arctic, lakes sometimes form suddenly when permafrost thaws and the ground collapses into a depression that fills with meltwater, only to disappear again just as abruptly if the surrounding permafrost breaks down further and the lake drains suddenly into the ground below. These thermokarst lakes are a striking, sometimes unsettling demonstration of how quickly a landscape long defined by permanently frozen ground can shift as temperatures change, releasing water and sometimes ancient organic material that has remained locked in place for thousands of years. The Murray-Darling Basin sustains agriculture across a vast, dry Australian landscape. Spanning much of southeastern Australia, the Murray-Darling River system supports a significant share of the country's agriculture, despite the region's generally low and unpredictable rainfall. Careful, often contentious management of water allocation among farmers, cities, and natural ecosystems has become an ongoing challenge, particularly during extended droughts when the river's flow can slow to a fraction of its usual volume. The basin stands as a clear example of the delicate balancing act required to share a limited, precious resource across competing needs, all dependent on the same uncertain rainfall. Cave pearls form in still, dripping water. Within certain limestone caves, small, rounded mineral formations called cave pearls form when a drop of water repeatedly coats a tiny grain of sand or debris with thin layers of calcite, and gentle turbulence keeps the growing pearl slowly rotating so that it develops evenly on all sides, rather than attaching to the cave floor like a stalagmite. These small, smooth formations, sometimes resembling polished stones, can take thousands of years to grow to just a few centimeters across, a patient, quiet process occurring in complete darkness, hidden from any eye that might otherwise admire it. The Rhine has shaped culture and industry across Western Europe, flowing from the Swiss Alps through Germany, France, and the Netherlands before reaching the North Sea. The Rhine has served as both a source of inspiration for centuries of poets and artists, and as a critical artery for European industry and trade. Its waters have powered mills, transported goods, and inspired legends of castles and river spirits that continue to shape the cultural imagination of the region. Efforts in recent decades to restore the river's water quality, following decades of industrial pollution, have led to a remarkable recovery of fish and wildlife populations along much of its length. Water can exist in a liquid state far below its normal freezing point. Under very specific, carefully controlled conditions, extremely pure water can remain liquid at temperatures well below the standard freezing point, a state known as supercooling. This occurs because ice formation typically requires a tiny impurity or disturbance to trigger crystallization, and in the complete absence of such a trigger, water molecules can remain in constant, restless motion, even in intensely cold conditions. This same phenomenon occurs naturally in certain high, cold clouds, where supercooled water droplets remain liquid until they encounter a tiny particle of dust or ice, instantly freezing into the crystals that eventually fall as snow. The Amazon River basin holds roughly 1/5 of the world's fresh water flowing to the sea. Beyond its title as the river with the greatest volume, the entire Amazon basin, encompassing the river and its countless tributaries, discharges an amount of fresh water into the Atlantic Ocean equivalent to roughly 1/5 of all river water reaching the sea worldwide. This staggering volume supports the largest rainforest on the planet, a vast, humid ecosystem entirely shaped by, and dependent upon, the immense quantities of water constantly cycling between river, cloud, and canopy across the entire basin. Groundwater and surface water are more connected than they appear. Though rivers and aquifers might seem like separate systems, they are, in most landscapes, deeply interconnected, with groundwater often seeping into rivers to sustain their flow during dry periods, and rivers, in turn, recharging aquifers when their water levels rise during wet seasons. Many rivers that appear to flow steadily even during long droughts are, in fact, being sustained largely by groundwater quietly seeping in from below, an invisible partnership between surface and underground water that keeps many rivers flowing even when rain has not fallen for months. Ice ages locked enormous amounts of water away from the oceans. During the peak of the last ice age, roughly 20,000 years ago, so much of the world's water was locked away in massive continental ice sheets that global sea levels were more than 300 feet lower than they are today, exposing vast stretches of land that are now submerged beneath shallow seas. Ancient human migration routes, including the land bridge once connecting Siberia and Alaska, existed only because so much ocean water had been temporarily redirected into ice. The story of human history itself has, in this way, been quietly shaped by the shifting balance between frozen and liquid water across tens of thousands of years. The Columbia River carved a landscape through catastrophic ancient floods. Toward the end of the last ice age, a series of enormous floods, caused by the repeated failure of an ice dam holding back a massive glacial lake, surged across what is now the Pacific Northwest, carving deep canyons and scattering giant boulders across the landscape in a matter of days. These Missoula floods, among the largest known floods in Earth's history, released more water in a single event than all the world's rivers combined carry in several years. The scarred, dramatic landscape they left behind remains visible today, a permanent record of water's power when it is suddenly and violently unleashed. The Ganges begins as ice within a Himalayan glacier. High in the Indian Himalayas, the Ganges River originates from the Gangotri Glacier, emerging from an ice cave at an elevation of over 13,000 feet before beginning its long descent toward the plains of northern India. As the glacier slowly melts and retreats due to changing climate conditions, questions have grown about the long-term reliability of this vital water source for the hundreds of millions of people who depend on the river downstream. The Ganges, born from ancient, slow-moving ice, carries within its very origins a quiet reminder of how closely rivers and glaciers remain linked, even thousands of miles from where the ice itself began. The water table rises and falls with the seasons. Beneath nearly every landscape lies a water table, the upper boundary of the saturated zone, where all the spaces between soil particles and rock are completely filled with groundwater. This level rises during wet seasons as rain and snowmelt seep downward, and falls during dry periods as water drains away or is drawn upward by plant roots and evaporation. In some regions, the water table lies just a few feet below the surface, while in arid areas it may rest hundreds of feet down, a slow, seasonal tide moving quietly beneath the ground, invisible but essential to the wells, streams, and wetlands that depend upon it. The Rio de la Plata is technically an estuary, not a river. Though often referred to as a river, the wide body of water separating Argentina and Uruguay is technically the world's widest estuary, formed where the combined waters of the Paraná and Uruguay rivers meet the Atlantic Ocean. At its widest point, it stretches nearly 140 miles across, so vast that early European explorers mistook it for open ocean. This blending of river and sea, occurring on such an immense scale, illustrates just how gradually and complexly the boundary between fresh and salt water can unfold in certain parts of the world. Some trees can pull water upward against gravity to remarkable heights. Through a combination of root pressure, capillary action, and the constant pull of evaporation from leaves, trees are able to draw water upward from their roots to heights of over 300 feet in the case of the tallest redwoods, all without the assistance of any mechanical pump. This process, called transpiration pull, relies on the cohesive properties of water molecules, which cling to one another strongly enough to be drawn upward in a continuous, unbroken column through microscopic vessels within the tree's trunk. It remains one of nature's most elegant demonstrations of water's quiet, persistent defiance of gravity, accomplished not through force, but through patient, continuous chemistry. The Pantanal is one of the largest wetlands on Earth. Spanning parts of Brazil, Bolivia, and Paraguay, the Pantanal floods extensively during the rainy season, transforming into a vast, shallow inland sea that supports one of the greatest concentrations of wildlife found anywhere on the continent. As the dry season arrives, the water gradually recedes, leaving behind fertile grasslands and concentrated pools where fish, birds, and other animals gather in remarkable numbers. This dramatic seasonal rhythm, an entire ecosystem expanding and contracting with the rain, has shaped the rich biodiversity of the region for thousands of years, patiently repeating itself with each passing year. Deep ocean currents move far more slowly than surface currents, while wind-driven surface currents can move at several miles per hour. The deep ocean currents that circulate cold, dense water around the globe move far more slowly, sometimes covering only a few miles each day. This deep circulation, driven by differences in temperature and salinity rather than wind, can take a single parcel of water anywhere from several hundred to over 1,000 years to complete a full journey through the world's oceans. Far beneath the waves, in complete darkness, water moves with an almost unimaginable patience, tracing a path that spans not seasons or years, but centuries. The Chao Phraya River sustains one of Southeast Asia's great cities. Flowing through the heart of Bangkok, the Chao Phraya River has shaped the growth and culture of Thailand's capital for centuries, its network of canals once so extensive that the city was sometimes called the Venice of the East. Seasonal flooding, driven by monsoon rains upstream, remains an ongoing challenge for the low-lying city, prompting extensive systems of dikes, pumps, and canals designed to manage the river's rhythm. The relationship between Bangkok and its river remains a delicate, ongoing negotiation, much like so many great cities that were built, quite deliberately, beside the water that sustains them. Cloud types reveal different stages of coming rain. Thin, wispy cirrus clouds high in the atmosphere often signal a change in weather still a day or two away, while towering cumulonimbus cloud,